Greetings to one and all. Thank you for joining in. We are gathered here today to honor the legacy of Sir Albert Einstein on the blessed event of his birthday. And this is SEDS KCT's Space Talk 9 on black hole discovery by LIGO. Now, I would like to welcome our honorable speaker, Dr. Jayant Murthy. Dr. Jayant Murthy is a senior professor at the Indian Institute of Astrophysics. He received his PhD in physics from the Department of Physics and Astronomy, Johns Hopkins University, Maryland, USA. It is worthy to mention that Dr. Jayant is one of those prominent scientists of the country who is popularizing science amongst the common folks for its deep and better understanding. I now welcome you, sir, on the behalf of SEDS KCT. Thank you for being a part of this event, and I request you to share your valuable insights and understanding with all of us. Sir, now please take up the session forward. Thank you.
Right, thank you for inviting me. So what I'm going to be talking about is the LIGO discovery, but more than that, just a general view of how it came about and what its importance was. Now, it was just over 5 years ago that the press conference was announced, February 11th, 2016. And it just so happened that the next day or a couple of days later, I was giving a talk on the frontiers of science in Mysore. And so I had a talk already prepared. But because this was so important, I asked them, would you like that presentation, or would you like me just to speak extempore on the LIGO event? So they said, yeah, sure, we'd like to hear about that. And I talked for about an hour with no slides, which I'm actually quite proud of. But so that was almost exactly 5 years ago, just a little over 5 years ago, that the first detection of gravitational waves was announced. And you can go to this YouTube video where Franz Cordova, who was the director of NSF at the time, they had a full 1 hour presentation on LIGO. So where did this all start? Well, it all started with Einstein, and here's the Animaniacs telling you
the theory of relativity has escaped me. It's all wrong, all wrong. I am a failure. Einstein is a dummy. Stupid Einstein, dummy boy.
Hey, Einstein! Whenever we're feeling blue, here's what we always do. When your face is long, sing the Acme song, you'll feel so fresh and new. There's the A, that's first, there's a C, that's next, there's an M, you're almost done. There's the E, it's last, now spell it out, A-C-M-E, that's fun.
No, backwards! There's the E, that's last, there's the M, it's next, there's C, you're almost done. There's the A, it's first, what's first is last, E-M-C-A, we're done.
Pretty good, Waggle, but your A always looks like a 2.
That's it. That's it. The theory of relativity. E equals mc squared. Energy equals mass times the speed of light squared. You kids is geniuses. E equals mc squared. E equals mc squared. E equals mc squared.
So that's how it all started with in 1905 with the theory of special relativity. And oh dear, this. So in classical relativity, that's Galilean mechanics, you have the standard bit about velocities adding. And so that leads to Newton's laws. So here is this picture of a guy jumping off a diving board onto a swimming pool in a moving car. And under normal circumstances, of course, you would dive off and you would go into the pool because your velocity adds. When you jump off the diving board, you have your own velocity plus the velocity of the car. And so you jump off, you fall in the pool. Of course, in this case, you have air resistance, and so because of the air resistance, you'll miss the trailer and fall onto the road. But that's a different matter. So basically, classical relativity is the mechanics that we all understand. It leads to Newton's laws, and whatever we do, we follow this classical mechanics. So the basic idea is that we cannot tell if we're moving or if we're in a sealed room. You can't tell. And so the problem with this, the problem with classical relativity, is that Maxwell's laws don't apply. Now, Maxwell, he identified light as an electromagnetic wave with a velocity of the speed of light, c, in a vacuum. But if you have a Galilean transformation, if you have now a room which is moving, now the speed of light will depend on your frame of reference. So no longer can you say that the physics is independent of the speed of whether you're moving or not. You can tell whether you're in a sealed room. So how do you check this? So first you have to measure the speed of light. And so you can measure the speed of light before modern technology. You could measure the speed of the first way to measure the speed of light was by looking at the eclipse of Io. Now, as the Earth goes around the sun, the moons of Jupiter go around Jupiter. And so if the Earth is moving towards Jupiter, then the moon will exit the eclipse a little bit sooner, because the light has to traverse a little bit less distance. If the Earth is going the other way, if the Earth is receding from Jupiter, then the eclipse is delayed a little bit. And so what Romer found in 1676 was that light took 22 minutes to cross the diameter of the Earth's orbit. And so based on that, you can get an estimate of the speed of light. Now, before modern physics, before the modern era, there was always a question of how light would travel. Because if you think about your everyday experience, you need a medium for any wave. If you think about sound waves travel through shock waves, or through waves, compression waves or rarefaction waves in a medium. So in either air or in water. So you need something to carry the waves. But light is different. Light is an electromagnetic wave, and now we know that there's no medium. But until the 1900s, there was speculation that there was an ether, and that light traveled through the vacuum in an ether. Now, if it travels through medium in an ether, then you would expect the velocity of light to be different depending on how we're traveling through that ether. So what Michelson and Morley, but probably it was almost entirely Michelson, what they did was they built a spectrograph or an interferometer. And here's the design of the interferometer. You have a source, and you have a half mirrored, you have a half mirror. The mirror is half silvered so that it reflects half the light and transmits half the light. And as the light goes and hits the mirror, one half of it is reflected up and the other half it goes through. And then when you measure it at the detector, you will measure refraction, you'll measure interference waves. You'll measure interference patterns because the distance is different. So now if the light travels according to the ether, then or if the light is transmitted by the ether, then depending on whether the Earth moves with the ether or opposite to or transfers to the ether, you expect a different speed for the speed of light. And so your interference fringes will change. So what Michelson did is that he took this apparatus and measured the interference fringes, and then he rotated it by 90 degrees and measured the interference fringes again. And what he found is that the speed of light doesn't change, regardless of what the Earth's motion was. Now, this fits into the Maxwell theory, where the speed of light is independent of the frame of reference. So in 1905, when Einstein had his annus mirabilis, his miracle year, when he came up with 5 superb papers, special theory of relativity, Brownian motion, I can't remember the other ones offhand, but 5 great papers. And one of them was the special theory of relativity. And so what he said here was that there's no preferred frame and that the speed of light is constant in all frames. So how is the speed of light constant in all frames? It's constant if you have, if the relationship between frames follows Lorentzian, follows the Lorentz Lorentz mechanics rather than the standard Galilean mechanics that we know. And so this leads to time dilation, it leads to the increased mass, and it leads to Lorentz contraction of distances. And so this was in 1905. This is Einstein's original paper, of course, in German, in that. Now, so the special theory is just a part of the general theory of relativity, in which you add gravitation. And so what Einstein did in 1915 was that he started with special relativity, and then he added the equivalence principle. And the equivalence principle is that you cannot tell the difference between free fall and no gravity. So if I'm now in that box again, as long as the box is moving uniformly, what Galilean mechanics will tell you is that I can't tell the difference between a box in uniform motion and a box at rest. What the general theory of relativity tells us is that we can't tell the difference between sitting in a box, which is in free fall, and a box with no gravity. Or we cannot tell the difference between an accelerating box and the force of gravity. So if you're sitting in a lift, if the lift is accelerating upwards, you feel heavier because it feels to you like the force of gravity is increased. If you're in a lift falling down, then your weight is decreased because the acceleration counteracts gravity. And so you can't tell the difference between an accelerating frame and gravity. And so Einstein was working through all of these formalisms between 1905 and 1915. He worked a lot with Emily Noether, who was a student of David Hilbert. He worked a lot with David Hilbert. And in fact, there was a competition between the two. But finally, in 1915, Einstein published his paper on general relativity. And in this, what he found is that the left, or what he derived, is that this G mu nu, this is the Einstein tensor, which is a description of the geometry of your object, of your space, is equal to 8 pi g, where g is the gravitational constant over c to the fourth, times this t, where this t is the energy momentum tensor. So what he found is that the gravity, or the geometry, is related to the energy momentum. And so this is the fundamental insight of general relativity, that your geometry is related to the energy momentum. And so the effect is that if you have a body like the sun causes a warp in space. So it causes the bending of space. And so one of the effects is this: if you're looking at the path of light, the path of light will be bent by any heavy object, like the sun. And so the actual position of the star is here, but as the light goes near the star, it's curved around. And from us, because we think that the light travels in straight rays, the actual position looks like it's here. So this is the bending of light. A common effect of this is if you look at distant quasars or at galaxies, you'll see the bending of the light from those distant objects by any object in the line of sight. So these are these Einstein rings, these Einstein rings where the light from a distant object is bent by a nearby galaxy. So one of the effects is the bending of light. Now, another effect, and this is what was first tested, this is the first prediction of general relativity that was tested, or one of the predictions of general relativity, is that Mercury's orbit, as we look at it, it precesses. And it precesses by 5,600 arc seconds every century. An arc second, there are 3,600 arc seconds in a degree. The moon is about half a degree in diameter. So this is something that's easily measurable, and it's something that people have known ever since the first telescope measurements in the 1600s or the 1700s. Now, of these, so they tried to figure out where this 5,600 seconds came from. Now, 5,000 seconds or so is easy. It's because the Earth itself is in a rotating coordinate frame. The Earth is going around the sun, and so as the Earth is in an accelerating coordinate frame, if we're trying to measure the orbit of Mercury, the orbit of Mercury will be affected by the Earth's own orbit, or by our own coordinate system changing. And so most of this is accounted by this. Pretty straightforward. Now you can account for another 500 arc seconds from the other planets, mostly from Jupiter. And so all of this people knew, and so they identified most of it, so they left 43 seconds per century unaccounted for. And so 43 seconds per century were unaccounted for. Now, this came just after Leverrier and Adams found Neptune. So the way they found Neptune was that Uranus's orbit could not be accounted for by standard Newtonian mechanics. So Uranus was shifting, and so when they what Leverrier and Adams did is that they said, well, why is Uranus shifting? It's because there's another planet there. And so they predicted the position of Neptune. And when Leverrier told his friend Gallo at the Berlin Observatory where to look, Gallo pointed the telescope there, and lo and behold, there Neptune was. So Leverrier was so taken with this that he thought, okay, well, if we can find Neptune this way, then we can find other planets this way also. And so what is this 43 seconds per century shift in Mercury? Well, it must be because there's another planet on the other side of the sun. We never see it because it's always behind the sun, but nevertheless, it's affecting the orbit of Mercury. And so he called this planet Vulcan, and kept looking for it, and there were people who said they saw it. Of course, now we know that there's no such planet. But now this was one of the predictions of the general theory of relativity. Einstein predicted that the orbit of Mercury would be affected by the bending of space near the sun. And so one of the other predictions of this was that, as I showed you earlier, the stars near the sun would be bent, so that the actual position of the star, the apparent position of the star, would be different from its true position. When you look at it, it looks like it's here, but it's really over here. You can't see this normally because the sun is bright and you can't see stars near the sun. But if there were a solar eclipse, then you could look and see, and you could look at the star field near the sun, and compare it with the star field when the sun was not in your line of sight, 6 months later. And if the stars looked like they had moved, then you would have a prediction of relativity. So this is what Einstein predicted. Now the problem was that the World War broke out, and so I think, if I remember right, there was an eclipse in 1915 in Russia, but no one could go there because of World War I. But there was also an eclipse in 1919. Now, this expedition was led by Arthur Eddington. Now, some of you may know of Eddington from his later fight with Chandrasekhar, which was quite bad. Chandrasekhar had predicted white dwarfs, and Eddington said, no, that's nonsense. And that seems to be one of the reasons why Chandrasekhar left England and went to the US. But in the early 1900s, Eddington was a famous astronomer. I mean, to the end of his life, he was a famous astronomer. Did a lot of groundbreaking science. Now, when World War I broke out, this was, of course, the German scientists were amongst the world's leading scientists. Much of the newest results came out in German, but this was difficult for the Allied astronomers, and so there was this whole issue of German science being bad and so on, and many of the German scientists were very patriotic, so this was another problem. Now, Eddington himself was a Quaker, part of the Society of Friends, and so the Society of Friends, they were complete pacifists. They didn't believe in war at all. Some of them said, okay, we'll work in war-related industries, but we can't go fight. Some of them said, no, we can't even work in war-related industry. We can't do anything to support the war effort. Eddington himself was an astronomer, and his friends in the government, they said, look, it would be a waste of resources to lock Eddington up, to put him in prison. Instead, why don't we use him on this eclipse expedition? So they planned this eclipse expedition, and they sent 2 teams, one to the Canary Islands where Eddington went, and another to Brazil where a colleague of his had gone. And so they measured the stars near the sun in those 2 locations. And here's a copy of the Illustrated London News from that time. And what they found was that the prediction matched Einstein exactly, or close enough. So this was an affirmation of the general theory of relativity. Eddington became famous and Einstein became famous. And just after the war, it was part of the reclamation of German science. So they said, look, Einstein is a German. He was opposed to the war. This is what he did. And so let's start making science international again. But more than anything, it affirmed Einstein's status as the world's leading scientists. Now, after this, once you have, so this is confirmation of the general theory of relativity in 1919. Now, one of the predictions of the general theory of relativity is that if you have accelerating masses, then you will get gravitational waves. Just in the same way, if you have accelerating charged particles, you'll get electromagnetic waves. If you have accelerating masses, you'll get gravitational waves. The first attempts to detect this were by Joe Weber at the University of Maryland. And what he used was just metal cylinders. He said if a gravitational wave passes by, then I can measure the deflection in these metal cylinders, and that will give me a measurement of the gravitational waves. Of course, we know now that gravitational waves are far too faint. Einstein himself never thought that gravitational waves would be measured. And we know that gravitational waves are far too faint to be measured, or far too weak to be measured in this way. Now, the first indirect measurements of gravitational waves, and until 2016, the only real measure, I mean, there were no direct measurements of gravitational waves, came from these binary pulsars. And so this was what a pulsar is the leftover from a supernova explosion. So you have a massive star, a star with a mass of over, let's say a mass around 10 solar masses. What will happen is that star, like the sun, it'll first burn hydrogen and then helium, and then it'll burn the helium to give you carbon, oxygen, nitrogen, and that's more or less where the sun will stop, with carbon, nitrogen, oxygen, because it's a fairly low mass star. But heavier stars, you now get they still have enough heat in the center that you go on past carbon and oxygen. You'll now get neon fusion and heavier elements until you get to iron. Now, iron is the most stable element there is. If you try to fuse iron, it'll take energy. If you for element below iron, you'll give off energy with fusion. For elements above iron, you need energy to fuse. They give off energy by fission. So iron needs energy to fuse any further. And so what will happen is that the interior of the star will cool very fast. The outer layers will collapse onto the interior and will bounce off at a substantial fraction of the speed of light, and you'll get a supernova. And what will be left at the center is, depending on the mass of the initial star and the conditions of the supernova, either a white dwarf, or if the mass of the core is heavy enough, greater than the Chandrasekhar limit of about 4 solar masses, Fermi degeneracy of the white dwarf will not be enough to keep the star from collapsing even further, and you'll get a neutron star, which is, as the name says, everything is comprised of neutrons. The total diameter of this neutron star is only about 10 kilometers or so, but it may have a mass of 4 or 5 solar masses. So the density is very high, elephants per teaspoon. Now, if you have one pulsar or one neutron star, the magnetic field is conserved, and so the magnetic field becomes very dense, and so because it's spinning very fast, you'll get charged particles that are going around trapped in the magnetic field. All these accelerating charged particles will give you a lot of electromagnetic radiation. Now, that electromagnetic radiation, because this pulsar is spinning so fast, because this neutron star is spinning so fast, will only be able to escape this neutron star through the poles. And so you'll get these beams of radiation. When these beams of radiation intersect the Earth's orbit, or if they intersect the Earth's orbit, you'll get a pulse. And so this is what Joyce Bell Burnell, what she found in the 60s, when she was looking with radio telescopes for these objects. She found these periodic pulses, and they didn't know what they were. This was in the 60s. And so the first they thought, okay, maybe it's little green men, maybe it's people outside, aliens trying to communicate with us. But soon they found more and more of them, and they finally understood that these were that this is what they were. they were neutron stars, which were giving out pulses of radiation. So if you have one of these, then it's spinning around, and the pulses are very regular. But now, if you have two neutron stars in a system, now these two neutron stars will be spinning around each other very fast. They'll be orbiting each other very fast. So now you have these accelerating masses, and so you get out gravitational radiation. Once you get out this gravitational radiation, that energy for these gravitational waves have to come from somewhere. So they'll come from the orbits of the neutron stars. So these neutron stars will start spinning around each other faster and faster as they lose energy, come closer and closer, and the pulses that you get will shift. They'll start getting faster and faster. So Hulse and Taylor in the early 70s discovered the first binary pulsar, for which they got the Nobel Prize. And this was a clear affirmation of the general theory of relativity. Here's the prediction of the general theory, and this is how the pulses went. Now, incidentally, we have many more confirmations of the general and the special theory of relativity from satellites. Your GPS unit on your mobile phone would not work unless unless you corrected for the orbit of the satellite, for both the special theory corrections because of the motion of the spacecraft, and because of corrections for general relativity because it's going around in the orbit of the Earth. So now people still, these are all indirect measurements of gravitational waves. So you still want to detect gravitational waves directly. Now, how do you detect it directly? Well, I told you that Weber tried to do it with these metal cylinders. And so he was looking for the difference in distance between the metal cylinders. But the amplitude is much too small for that. So what they started doing, they started exploring new ways of doing it in the 60s. And the main people behind this were Weiss, Kip Thorne, and Barry Barish. Raymond Weiss, Kip Thorne, and Barry Barish. And there were other people involved. So they first started in the 60s, and there was a lot of theoretical work. How do we do this? Because you can't just, as I said, you can't just take cylinders and hope to detect the gravitational waves. So they were calculating the amplitude, and then they were working out how to do it, and then they were looking at ways to drop the noise to see how you might measure it, and all of this. It started in the 60s, and this is really an example of sustained science. When you're trying to do science, there's a lot of false avenues. You go in one way, it just doesn't work. Maybe you don't have the computational ability because computers now are so much better than they were. You don't have the instruments. You don't have the capability. Maybe lasers in the 60s, the first laser was, I think, in the 50s. Lasers in the 60s weren't as advanced as lasers we have now. And so there's a complex, or you have to, science can only advance with technology. And much of technology advances because of the requirements of science. So you have people working to say, how can I go to the extremes? How can I go to the next millionth of a degree above absolute zero? How can I measure the speed of light to the 10 to a trillionth of a percent? And so the only way you can do this is by advancing the technology. And so this is the way it was for LIGO, that the only way they could do it was by a sustained effort over 50 years, from the 60s to 2015. Now, all of this takes money. And so again, this calls for a sustained commitment at the government level. You need people to say that, I know you're not going to make any real progress for the next half century. But that's okay. We know that the results are very important, and so we are going to make that commitment to you for the next half century. And so that's what NSF, the National Science Foundation, did. They made that commitment to LIGO. They kept on funding them. Of course, there were false starts. Of course, there were problems in money here and there. Some people didn't understand how important it was. But whatever it was, finally, they did get that groundbreaking detection that did lead to those 3 Nobel Prizes. And so here's a picture of LIGO. These here's the schematic. So each of these arms are 4 kilometers long. There's a test mass at the end of each, and beam splitters and precision mirrors that are mounted on these carbon fiber spider webs so that they can detect small motion. So if I remember right, the amplitude from that gravitational event is something about the size of a proton. So you have to detect a distance, you have to detect a deviation of about a size of a proton over these 4 kilometer arms. So you can understand how much technology goes into that. It's just not easy. So as I said, this started in the 60s. The first LIGO observations began in 2002. And from 2002 to about 2015, they were working with LIGO, and it was just not sensitive enough. They couldn't detect anything, but they kept on improving techniques. They kept on improving the instrumentation. And then finally, advanced LIGO came on in 2015. And the first detection was on February 11th, 2016. Now, I'll describe the detection itself in a little bit, but they had to go through all sorts of quality checks. So this was a multi-institutional effort with hundreds of scientists, if not thousands. And so they had these different groups, and they did many different things. So they had 2 detectors. They had to make sure that the signal was reproduced in both detectors. They had groups who would introduce, without telling anyone else, they would introduce fake signals into the data and see if that came out. And they would let people go all the way through. They would let people analyze the data. They would let people write the paper. And then they would say, no, this is fake data, so don't publish. So they went through extraordinary checks. And finally, the first observations were actually detected. I say first detection, but that was really the publishing of the paper. The first detection was actually within the engineering data itself. They found these fluctuations within the engineering data, and so they checked it, they double checked it, they went through everything. They had multiple people looking at it, and finally they decided that no, this is real, and so then they published. Now I remember the whole procedure. This was not really the way I think science should be done, but anyway, maybe for a first event, they wanted to make it a big public relations event, because it is really exciting. When you detect gravitational waves for the first time, it is very exciting. And so they had a press conference. They had an embargo before the press conference. Of course, the rumors were out there, and so most of us knew more or less what they had discussed. But still, it was still an exciting press conference. And when the news came out, it made the headlines everywhere. And so what they actually did discover was 2 black holes with masses of about 30 solar masses. Each black hole was about 30 times the mass of the sun. And the 2 black holes, as they were orbiting each other, and as they orbit each other, they give off gravitational waves. And finally, they collide. And so what they detected was the gravitational waves in the last millisecond or maybe a second before the actual collision. And so this will have a shape. This profile, the gravitational waves that you see, will have a shape depending on the predictions of general relativity. And many of the people who worked on that, including these detections, Professor Vishwamitra, they were from India. So there was a big Indian contingent involved in this. So now this is LIGO. So now they're continuing to improve LIGO. They take LIGO down every now and then, and they improve the capability so that they become more sensitive, so that they can detect other frequency ranges. And they're adding more observatories. There's one being added in Italy, the Virgo LIGO, and there's one in Japan, Cabra, and there's one that's going to be in India, and I'll show you that on the next slide. So these are all added onto the Earth, and the advantage of having more observatories on the Earth is that now you can do better pointing. When you only have two detectors, then you can't do centroiding. You can only you can't do this trigonometric stuff. So all you can do is just say that it falls anywhere within some area of the sky. And the way you do that is that you say it hits this detector first and it hits this detector later. So therefore, it must be it must be from this direction off in the sky, and it must be at this distance. But now if you have three detectors, now you can triangulate. And so you can say, okay, it must be within this box. And of course, the more detectors you add, the better positioning you get, and the better sensitivity you get. But no matter what you do on the Earth, you're limited to in your frequency range, because you can't get much greater than 4 kilometers or so. Your technology gets difficult. You need the space, and so you just can't do that much better. And you're limited by the Earth itself. The Earth always has seismic events. There's always earthquakes. There's always North Korean nuclear explosions. So any of these will cause these disturbances in your data. And so you have to separate that from your actual signal. And it's always difficult. So you're limited in the space, in the frequency space that you can cover. So one of the very imaginative ideas, I thought, was LISA, which was 3 spacecraft that went out into space. Now, these spacecraft would maintain their distances. They had little thrusters on board that would maintain the distance between them. And they would measure that distance very precisely with interferometry. And anytime a gravitational wave came by, it would change the distance between these spacecraft. And so now you would get you would be able to measure the you would be able to measure the amplitude and the frequency of your gravitational wave. So LISA was originally proposed in the 1980s, but because of funding cuts, it never actually flew. The Europeans flew a trimmed down version of LISA, the LISA Pathfinder, just to show that the concept would work. And indeed, it does work well. And so now, with the excitement about gravitational waves, hopefully they will fly LISA at some point. So what I will end with is LIGO-India. Now, within a few minutes or maybe a few hours after the LIGO detection, LIGO-India had been going on for some time. And with the primary people being people like Bala Iyer at Raman Institute and Tarun Saradeep at IUCAA. So there were many institutions involved, and they had proposed this to the government. And of course, it was sitting with the government for some time because it was a lot of money. But they did have a basic proposal in shape. Now, once LIGO detected the gravitational waves, now this, of course, it's a major international event. And so the government of India decided that this is indeed a good thing. And so within a few hours after the first detection, they made an in principle approval of the proposal. And so now it's been going on. Of course, things always go slower than you would like. And so in the 5 years since the first detection, they've now identified the land and probably will start building soon. And what it is, it's just a basic copy of the LIGO USA. They'll get the detectors, and they'll build it in India. Then they'll incorporate it into LIGO-India. And so once LIGO-India, it's going along well. Once that's fully built, then India will also be a part of this new era of gravitational wave astronomy. And so what I'll end here is by saying that for so many years, we've really been doing optical astronomy or electromagnetic astronomy. We've looked at, we started with optical, we did radio waves, we've done ultraviolet, X-rays, gamma rays, but all electromagnetic. Now recently, these new areas have been opening up. Gravitational wave astronomy, neutrino astronomy, and who knows, when you open up a completely new area of science, who knows where that will take you. So let me end here, and I'm happy to take any questions.
Professor, I have a question.
Uh-huh.
Am I audible, Professor?
Mm-hmm. Yes,
okay.
I can hear you.
So I want to ask that at the outset of the presentation, we know that there is a precession in Mercury's orbit.
Okay.
Okay. So does that mean that the funnel which it's creating in the space-time fabric because of the curvature, does that mean that that curvature is also changing with time?
They remember that that the curvature in space-time, it's due to every individual planet. So now you have the sun itself. The sun there are all sorts of complications here. See, the sun is not going around the center, right? The sun is going around the center of mass, which is a little bit outside the sun. Again, largely because of Jupiter. So the sun itself is in an accelerating system. The sun is rotating about the center of mass. So that will change. Mercury is much smaller, but yes, Mercury is accelerating around the sun. And so whatever perturbations it causes will also change. And so
does that
you will constantly get gravitational waves.
Okay. So does that mean that every planet which is in the solar system is like there is a precession in every planet's orbit, like Mercury's?
Absolutely.
Because there is a center of mass between every planet and the sun.
There will be a precession, but the further away you are from the sun, the less the effect.
Yeah, exactly. Okay. And I have another question, Professor. Mm-hmm. May I ask?
Mm-hmm.
In the end of the presentation, when you were suggesting about your idea, which you thought about spacecrafts in space, which had these detectors, LIGO detectors. So the difference that the gravitational waves make is about the size of a proton.
Right.
And you said that the spacecrafts will be affected by the gravitational waves, and you can measure that distance, that difference between the spacecraft. So will it be easier to measure that distance because it's so small, almost the diameter of a proton?
So I'm at a complete loss to understand these technology innovations that they've made. I just don't understand even how you can measure a deviation the size of a proton on the Earth, because I would think that anytime someone even walks by, I think there's a lot of noise in the background, or someone would.
It's someone else's, Professor.
Yeah, whoever it is, if they would mute. Okay, so even on the Earth, I just don't understand how they manage to. I mean, technologically, I know how they do it, sort of intellectually. But emotionally, I can't understand it. And so when you say in space, yes, I don't know how. But what it does open up is that it opens up different frequencies. See, on the Earth, you're limited because you can only make your detector so large, 4 kilometers, 10 kilometers, maybe. I mean, I don't know. But on space, what you can do is you can open it up make it huge, 20,000 kilometers, 100,000 kilometers. I mean, again, limited by your technology
but then there is the question that will the government allow it?
Will the government allow it? Why?
I mean, there is a question. That's the question, because sometimes they have problems with projects like these. So
well, the only problem is funding.
Yeah.
And this is it's a serious problem for all of us. Science funding has been cut worldwide. In India, more, except for China. One of the reasons Chinese science is going ahead so fast.
Yeah.
But in India, certainly, it's been cut to about half of what it used to be, and it's going to be very difficult.
Okay, I have another question, Professor. I'm sorry for the questions, but may I ask?
I have no problem. Keep going.
Okay, it is about black holes, and I may be mistaken about it, but yesterday I was conversing with a PhD student in Russia, and she was talking about something that the universe is sort of oscillating between a singularity. Like Roger Penrose recently got the Nobel Prize for that. Where does the research stand on that?
I mean, Penrose got the Nobel Prize for really showing that black holes are a common occurrence. Not so much for universe oscillating or anything else, more of showing that black holes are a common occurrence. Now, what has happened in the universe over the last, let's say, 20 years, is that before we thought that the universe was steadily slowing down, the deceleration of the universe, because of gravity. So it formed in a big bang, and the universe started expanding, and it's slowing down slowly. So eventually, who knows what would have happened? Would it have continued to slow down exponentially? I mean, exponentially down, or would it have contracted again? Now we know that the edges of the universe are expanding. This is the cosmological force.
Yeah.
The dark energy. So there's no question of the universe oscillating anymore. Now the universe is expanding.
Yeah, exactly. So does that mean that someday this gravitational expansion will overcome the other three forces? Nuclear.
What they, again, this is all speculative, but what seems to be the case now is that what will happen eventually is that the universe continues to expand, stars continue to die, and eventually we'll be left in an isolated volume of space with nothing to see.
Yeah.
Or maybe some of the theories I've seen is that the dark energy increases with time. Right now, dark energy, you only see dark energy on very large scales. But who knows? Maybe you'll see dark energy on, maybe as dark energy increases, maybe it'll affect us individually. So we'll suddenly expand.
Even at the quantum levels?
Even at the quantum level. Sure.
Wow.
Yeah, that's some of the theories. I mean, all theories, right? So how do you know? You have to look and see what predictions they make, and do they fit the predictions?
Exactly. And sir and Professor, where does string theory stand at this subject?
I'm a string theory skeptic myself, because string theory has undoubtedly made many contributions to science. But even now, we have no way of detecting a string. We have no positive evidence for strings.
As far as I remember, I have been reading about string theory a lot lately. Professor Brian Greene once was talking about on it, and he said that the energy levels that we are dealing with in string theory are 19 orders of magnitude larger than what we have today at CERN, at Geneva, Switzerland. So maybe we do have a shot at this.
See, again, I have no way of ruling it in or out.
Yeah, exactly. Neither of us do.
Science is an observational field. It rests on data. And as far as I know, there is no data to support strings, and perhaps no data to say that strings don't exist. So I don't.
Exactly. Exactly. Okay, Professor, it was really honor honorable to speak to you. I'll be muting myself now. Bye.
So there are few questions in the chat.
The vector direction of the pulsar loses
Shall I read it out,
when
sir?
receiving radiation. Does the gravitational momentum increase as the diameter of the star increases, or as the pulse duration increases?
Shall I read out the question, sir?
Yeah.
Ravinder R asks, when a pulsar loses energy via pulsating radiation, does the rotational momentum increase as the diameter of the star decreases? If so, the pulse duration increases.
No, nothing happens to the neutron star. The neutron star is a fixed radius. It's just determined by the you can't squish neutrons any closer together. So you might get occasional changes because of star quakes. The matter redistributes a little, but the energy loss is the loss the rotational energy. The pulsar rotates slower, so it doesn't change the diameter, but it changes the speed of rotation, the angular velocity of the rotation.
Thank you, sir. The next question is by Bhargavi Patel. What is Lorentz contraction?
So when you're going, if you're as your speed increases, then the time will the if the apparent the length in your frame of reference will shrink. So as an object is going away from you fast, it'll look shorter. So that's Lorentz contraction. And it's just because of the way that the light, when you apply the formulae for the shift in frame, you get time dilation. The time gets longer, and the length gets shorter.
Okay, sir. The next question is by Krishna Priya. Good afternoon, sir. I'm interested in doing MS in astronomy and astrophysics. Will I get a job in ISRO?
Well, now these are two completely different things, because ISRO is largely a space agency. They're not so much a science agency. There are people who do science in ISRO, but the primary focus of ISRO is to launch missions. And so with an MS in physics, I don't know. I'm sure they do take people, but I have no idea. If you want to do astronomy research, then you need a PhD in astronomy. But most of ISRO's staff are actually engineering people, so they have MTechs or BTechs or MTechs, not or B engineering. Not so many science people.
Okay, sir. The next question is by Saktivel. Good afternoon, sir. I had a doubt. Is the speed of expansion of this universe greater than the speed of light?
No, it's not. Nothing is faster than the speed of light. Now, what happened at times is that you had inflation. And so what happens in inflation is that the universe just gets bigger. You have two objects that are close together, they're in contact, and then you have this period of inflation in which you're creating space between those two objects, and now those two objects are far apart. But at no time are you traveling faster than the speed of light. Nothing can go faster than the speed of light.
Okay, sir. The next question is by Ashwin. Thank you, sir. Is it possible to determine the age of the universe through gravitational waves?
In a sense, if you can hope to detect the Big Bang in gravitational waves, then yes. But I have no idea what the amplitude is or how you would do it. But sure. But I mean, I suspect that there's so much other stuff around that no, you can't.
Okay, sir. The next question is by Vedant. Sir, the method of formation of black holes you described was really fascinating, but I don't understand how we are able to make such predictions. Are these verified or just theories?
Right now they're only theories. We don't know. I mean, we have not seen a stellar mass black hole. But we do understand the physics. We have seen many of the byproducts. So we've seen white dwarfs, we've seen neutron stars, and so if you have more material than can be held up by a neutron star, you will get a black hole. So right now those are theories. Now, how do these 30 mass black holes form? Those are likely to be these stellar mass black holes that have collided. So if you're in a dense environment, such as in a globular cluster, then you will get collisions between black holes, and you might get larger and larger black holes. So no, we have not seen this process occur, but we are confident that this is what happens because of ancillary evidence. We have other things that we have predicted and that we see.
Excuse me, Professor, I have another question.
Mm-hmm.
Why is it not possible to reach absolute zero?
So we can get close to absolute zero, but absolute zero means that there is no energy at all. And finally, you're always going to be limited by quantum mechanics. You're always going to get some quantum fluctuations. So that will give you a temperature.
So is it because it will violate the uncertainty principle?
Uncertainty principle, exactly.
Okay. Okay. Thank you, Professor.
Next question is by Lakshmi Bharadwaj. So we know our universe is expanding because of what we call the dark energy. Is it possible for it to start contracting again as its previous counterparts, the universe that existed before us?
So let me address the last part first. We don't know that there's any universe that existed before ours. As I had said earlier, astronomy or science rests on data. And so how do we know, how would we ever know that there was a universe before us? It's a metaphysical question. It's a philosophical question. So that's the first part of it. Now, the second part is that as far as we know, or as far as we know that the universe is because of we observe supernovae at the edge of the universe that are expanding, that are accelerating away from us. So we know the universe is expanding. We have not come across any reason to say that the universe will start decelerating again. So as far as the physics that we know now, given that we don't really understand dark energy, as far as the physics that we know now, no, the universe will never decelerate.
Okay, sir. Is there any relation between dark energy and dark matter found? Any observation evidence?
No, there's not. The names are purely, in a sense, coincidental and badly chosen. Dark matter was it's the matter that we know is there because of gravitational effects, but we don't see because it doesn't emit light. What it is, we don't know. There's speculations, but we don't really know what it is. Dark energy is this energy that's forcing that's counteracting gravity. So dark matter adds to gravity. Dark energy counteracts gravity, and so no, we have no way of knowing. I mean, there's no relation between the two. Sorry.
Sir, excuse me, sir. Further adding towards the question.
I'm sorry.
Hello.
Yeah.
So, further question is like there was no ether when we came out to found that there is only vacuum. Like that, is there any chance that dark energy might not be? I mean, that dark energy theory is nullified. Is there any chance?
So people are, as always, people try different ways of explaining this. So maybe this modified Mond theories, this modified Newtonian dynamics, but so far what we found to be the evidence, we always have to rest on evidence. And so far, most of the evidence is in favor of dark energy. It may be that someone will come up with some theory that explains it without dark energy, but now this is all we know. So the simplest way to explain it is with dark matter and dark energy.
Thank you, sir.
The next question is by Ravinder. Once the fusion at the core of a star stops, it should just gravitationally collapse in, right? But why the matter is shot outside a star?
So for most stars, yes, it just collapses. So for a star like the sun, it'll just contract and not gravitationally collapse because the cooling will be slow, but it will contract and give you a white dwarf. But for a very massive star, what will happen is that the transition between fusion and not fusion is abrupt. So you have this iron in the core, and once the iron starts to fuse, then it'll suddenly start absorbing all that energy. And so the interior of the star cools very fast. And so the outer layers, now there's nothing to keep them up, because before they were being kept up by thermal pressure, but now there's nothing to keep them up. So they collapse, and they collapse at a substantial fraction of the speed of light. They come down and they hit the essentially solid surface of the core. And so when they hit that, they rebound. It's just a classical mechanics. They come in, they hit the surface of the star. Of course, they're traveling at a substantial fraction of the speed of light, maybe a third of the speed of light, and then they just bounce back out. So it's only for the heaviest stars that you will get this supernova effect.
The next question is by Lakshmi Bharadwaj. Sir, Nobel literate Sir Roger Penrose mentioned that there was a chain of universes. Is it mathematically proven or just a theory?
No, again, this is a philosophical speculation. So we only have the one universe as far as we know. We have no way of detecting other universes. There are people who say that maybe you can detect fluctuations from other universes. And these are all theories that are being tried out. But so far, no evidence.
Excuse me, Professor.
I
have another question. Stephen Hawking, in his equation about entropy of a black hole, he has the Planck's constant, the reduced Planck's constant, and the gravitational constant both multiplied together. I mean, he has the two constants which should not be together in an equation multiplied together. Does that mean that he somehow unified the two theories, the two realms?
No, I don't know what equation that is. But no, I don't know at all.
The equation goes like.
But there's no unified constant. There is no unified
Boltzmann constant multiplied by speed of light cube divided by 4 times reduced Planck's constant times the gravitational constant.
Yeah, I have no idea what the context of that is. So let me not comment. But no, there is no unified theory.
Okay.
That much I can tell you.
Next question is by Vedant. Sir, is there any equation that predicts life outside Earth? I remember reading something like that.
The only thing that you have is the Drake equation, but that's not a prediction of life outside Earth. That's just a way to estimate if there's life outside the Earth or not. So no, there's no theory that says there must be life outside the Earth.
Professor, one last question. What is actually the metric tensor?
Which tensor?
Metric tensor.
Metric tensor, it's just an equation that describes the geometry. So you apply it in your normal thing, you might have x squared plus y squared plus z squared is equal to the radius squared. When you add time, x squared plus y squared plus z squared minus t squared is equal to a constant, and so on. It's just a way of describing the geometry. That's all it is. So you can have different tensors. You can have Riemannian geometry. You can have Kerr geometry around black holes. But that's all it is. It's just a way of describing the geometry. And so when you do your equations, you then apply.
Okay. Is it the same with the Ricci-Covici tensor too?
The Ricci tensor, yes, that's another gravitational thing. It's a way of describing the geometry of space. These are just different formalisms.
Thank you, Professor.
It doesn't change the physics. It's just a formalism.
Okay.
There's a question by Adarsh. Drake's equation. It's a probabilistic equation.
Yes, that's right. It's just a probability of finding life. Yes, that's all.
Okay.